All right, so now we're in a position where we can actually apply this angular overlap method to practical problems. So, we can choose many different types of correlations. Uh, there exist many different types of correlations, right, between different geometries. The simplest, or one that we've already talked about, which I think it's nice to show how this theory um, handles it, is the octahedral to tetrahedral transition. Remember, we came up with a relationship that the orbitals were essentially just flipped, right? Um, the EGs, which are now renamed to be E, are in tetrahedral became lower in energy, and the T2Gs in octahedral became the T2s, but they're higher in energy. And we said that delta T was 4/9 the value of delta O. So let's do that with angular overlap method and see what happens. So first we consider the octahedron. And so that is ligand positions 1 through 6. And for each d orbital, we are going to figure out the E sigma and E pi total energies. And so we go here and we go for the z squared, dz squared, and we're positions 1 through 6 here for octahedral. And so we look at all the sigma angular scaling factors, and we're going to add up 1 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1. That equals 3. So the dz squared in an octahedral environment is worth 3 in E sigma. Then we do the same thing with E pi, and you can see dz squared actually cannot do any pi bonding in any of these positions, so it gets zeros, and so that gets 0 E pi. So overall, the energy of a dz squared orbital in octahedral environment is 3 E sigma. So you can go through this and figure out for x squared minus y squared, the energy is also 3 E sigma, right? So you could go back to this diagram, and here we're going to have, for E sigma 0, 3/4 plus 3/4 plus 3/4 plus 3/4 plus 0, that equals 3 E sigma. And then pi is 0, 0, 0, 0, 0, 0. So it's also 3 E sigma. That should not surprise you. After all, we know the dz squared and the x squared minus y squared in OH symmetry are degenerate. And then you can do the same thing with xz, yz, and xy. You figure out that those are all triply degenerate, as you expect, right? They transform as T2G, and they all have an energy of 4 E pi. That is what we call delta O, the difference between those, okay? Now you do the same thing with tetrahedral. And so now you're going to go here, go to tetrahedral, which is atoms 9 through 12. You go on this table and you start adding things up. Okay, z squared, is going to be 0, 0, 0, 0 for E sigma, and 2/3 plus 2/3 plus 2/3 plus 2/3 for E pi. That gets you 8/3, and that's what's showing down here. So you can go through all this and just sum it up on the chart, and you're going to get these differences. Now, remember that E pi can be positive or negative. We don't know. It depends upon is it pi accepting or pi donating ligand. Pi accepting will be negative. Pi donating will be positive. E sigma, there's no such thing as a pi accepting ligand. You can't break a sigma bond like that. So you're just going to have pi donating. So E sigma is always going to be positive, and the magnitude of E sigma, because sigma bonds are greater than pi bonds, is always going to be bigger than E pi. So you can safely say that 3 E sigma is going to be greater in energy than 4 E pi, and similarly 4/3 E sigma plus 8/9 E pi, that's going to be greater than 8/3 E pi, right? So that's delta T right there, the difference between these two states. Now you can do a little bit of math here, rearranging. Let's calculate delta T. That's going to be 4/3 E sigma plus 8/9 E pi minus 8/3 E pi. If you work out that math, you're going to get 4/3 E sigma minus 16/9 E pi. Then you factor out a 4/9 from this expression. You get 4/9 times 3 E sigma minus 4 E pi. Well, what is 3 E sigma minus 4 E pi? That's the definition of delta O, 3 E sigma minus 4 E pi. So we just proved here, using the angular overlap method, that the magnitude of delta T is always going to be equal to 4/9 delta O. Pretty cool. So I promised I would show you where that came from.